All right, so let's go ahead and look at 20. We want to use the solid enclosed by the paraboloids y equals x squared plus z squared and y equals x minus x squared minus z squared. So here we have the region that's enclosed by the two paraboloids, y equals x squared plus z squared and y equals 8 minus x squared minus z squared. So here you have basically the shape of, what our object is, and we want to find the volume of this object. And so all we're really going to do is we're going to be able to define the two planes. And so again, we're going to define our two planes using the y-axis. And so our y is going to be first, and then what we can do is then determine, okay, where do they intersect, and that will help us with our z and our x's. All right, so let's go ahead and do that. So I'm going to go ahead and define the region again. So I'm going to define the region D, and then the inside region is going to be defined by y, and so it looks like the furthest right we go is going to be 8 minus x squared minus z squared, and then the lower half of that's going to be x squared plus z squared, and then it's going to be dy, and then we'll have dA. That represents, the region that's going to be on the xz plane. All right, so let's go ahead and write this up here. And so again, here's our region. 8 minus x squared minus z squared, and then x squared plus z squared is the lower half of our integral. dy, dA. Let's go ahead and integrate that. This is going to be y 8 minus x squared minus z squared, x squared plus z squared. Again, you can just go ahead and kind of skip what I just wrote and just wrote out what we're going to have. And so we're going to have, the double integral of 8 minus x squared minus z squared minus x squared minus z squared dA. All right. So we do that. We're going to get our double integral. And on the inside, we're going to have 8. And then it looks like it's going to be minus 2x squared minus 2x squared minus 2z squared. dA, and I'm going to rewrite that just a little bit more so that you can see what we're going to do. So the double integral, we could pull out, a 2 if we wanted to, but I'm just going to show it this way. 8 minus 2 x squared plus z squared. Now let's look at the intersection between x squared, our two parabolas. Well, if we look at the intersection, let's go ahead and set the two equal to each other. So it's x squared plus z squared is equal to 8 minus x squared minus z squared. Bring the x squareds and y squareds over. We're going to get 2x squared plus 2z squared equals 8. Divide everything by 2. We get x squared plus z squared equals 4. So there's the intersection. So we could project this on the xz plane. And so it looks like, oh, hey, we have a circle of radius 2. And so again, I can say x is r cosine theta, z is r sine theta, and x squared plus z squared is equal to r squared. So now I'm going to change this to spherical coordinates. And so we're going to go from 0 to 2 pi. The radius of our circle is 2, so from 0 to 2. And we're going to have 8 minus, remember, x squared plus z squared is just r squared, so 8 minus 2 r squared, r dr d theta. Don't forget that r dr. It's very easy to forget, so please just don't forget that. So we have 0 to 2 pi. I'm going to go ahead and I can pull out the theta now, so d theta, and then 0 to 2, 8 minus, 8r minus 2r cubed dr. And now let's go ahead and integrate. So again, The first part's just going to be 2 pi. And then when we do the integration for r, it's just going to be 4r squared minus 1/2 r to the 4th from 0 to 2. Plug in 2, we're going to get 2 pi times, so 2 squared, so 16 minus, another 16, but 8, so 8. 16 minus 8 is 8. 8 times 2 is going to be 16, so 16 pi. And we're finished. All right. So hopefully, today's notes weren't too bad. Again, we're just doing triple integrals. You need to